Let's dive right into this explainer and demystify an algorithm that sounds like it literally shouldn't work at all. We are talking about a model that makes an assumption so blatantly incorrect, you'd think it would just immediately crash and burn in the real world. Yet, surprisingly, it powers some of the fastest and most efficient classification systems we have today.
It's a crazy starting premise, right? A mathematically incorrect assumption that somehow wins anyway. But honestly, that is the true beauty of naive Bayes. It teaches us something incredibly fundamental about machine learning. Sometimes, the absolute best model for your data isn't actually the most mathematically correct one.
So this is the central mystery we're going to solve today, especially when we look at high-dimensional text classification. How exactly does a model built on a completely flawed foundation consistently outpace and outmaneuver theoretically superior, quote-unquote, smarter algorithms?
Let's get into part one, the beautifully wrong assumption.
Picture this. You're trying to sort emails into spam or not spam. To do this, you're using every single word in the vocabulary as an individual data point. Suddenly, you've got tens of thousands of dimensions to work with, but probably only a very limited set of actual training data. Well, most smart classifiers absolutely choke here. Logistic regression needs a massive amount of samples to reliably estimate thousands of weights. Decision trees start splitting on one word at a time and just wildly overfit. And k-nearest neighbors? In 10,000 dimensions, it becomes totally meaningless because every single point is basically equally far from every other point. But Naive Bayes, it handles this effortlessly, scaling to millions of features and training in a single pass.
Moving right along to Section 2, Flipping Probabilities with Bayes.
To really understand how it survives these massive feature sets, we've got to look under the hood at the math. At its core, we're just calculating the probability that a document belongs to a certain class based on the specific words inside it. Bayes' theorem flips conditional probabilities around. It takes the likelihood of seeing those specific words in a class, multiplies it by the prior probability of that class existing in the first place, like how common spam is overall, and then divides it by the overall evidence. The class that gets the highest resulting probability takes the win.
But here is the absolute crucial point, the core assumption. The algorithm treats words like machine and learning as completely independent and completely unrelated. Now, to compute the exact true probabilities for a 10,000-word vocabulary, you'd need to estimate a joint probability distribution over 2 to the power of 10,000 combinations, which is impossible. So Naive Bayes just skips that and assumes every feature is completely independent. It's obviously wrong. Words like machine and learning are heavily dependent in real documents, but it does it anyway.
Which brings us to Section 3, Why Being Wrong Works.
Okay, let's actually solve this mystery. Why does this incredibly flawed assumption lead to such great predictions? Well, it boils down to 4 key reasons. First, ranking over calibration. We don't need perfect percentages. We just need the top-ranked class to be correct. If it calculates a 99% probability of spam when the real probability is only 70%, it still correctly flags the email as spam. Second, high bias, low variance. This massive independence assumption acts like a super strong constraint that stops the model from wildly overfitting. With limited data, a stable, slightly wrong model will absolutely beat an unstable, right one. Third, correlated feature redundancy actually cancels out. If machine and learning always show up together, the algorithm double counts the evidence, sure, but it double counts it for the correct class. And fourth, sheer speed. Prediction is just lightning-fast matrix multiplication.
All right, let's check out Section 4, 3 flavors of Naive Bayes.
Because, yeah, there isn't just one single version of this algorithm. It's honestly more like a toolkit, and you've got to know which tool to pull out. If you've got word counts or frequencies like TF-IDF values for email spam, you're going to want multinomial naive Bayes. Now, if you are dealing with continuous values that look like normal bell curves, say tabular sensor data or iris flower measurements, you use Gaussian. And if your data is purely binary, just zeros and ones, which is absolutely perfect for super short text like SMS spam, where you only care if a word is there or not, you go with Bernoulli.
Moving to Section 5, Fixing Real-World Flaws.
Now, in the real world, being this naive means you need a few brilliant mathematical hacks so the whole thing doesn't just shatter. Think about encountering a brand new word in a test email. Let's say the word is discombobulate, and the model never saw it during training. The probability for that word drops straight to 0. And since we are multiplying probabilities together, one single 0 destroys the entire equation, wiping out all the other evidence. Laplace smoothing elegantly fixes this by adding a tiny count, usually an alpha of 1, to every single feature, so that literally nothing ever hits absolute 0. Then you run into another huge headache, floating point underflow. When you multiply hundreds of tiny probabilities together, the resulting number becomes so microscopically small that the computer just shrugs and rounds the whole mess down to absolute zero. The product just disappears completely.
So the fix for this? Computing in log space. Instead of multiplying all these tiny fractions, we just take their logarithms and add them together. This completely prevents the underflow issue. And even better, it magically converts our complex multiplication into simple addition, turning the whole classification into a hyperfast dot product matrix multiplication.
When you map it all out, the final classification pipeline is just beautifully simple and blazing fast. You count up your frequencies, apply your Laplace smoothing so a zero doesn't wipe you out, compute your log probabilities using some basic matrix math, and simply return the class with the highest score. You can train this in seconds, even on 1,000,000 documents.
And finally, Section 6, Naive Bayes in practice.
So, how does our delightfully flawed hero stack up against the competition in a direct showdown with something like logistic regression? Well, naive Bayes is a generative model, while logistic regression is discriminative. This comparison perfectly highlights a really solid rule of thumb. Because of its strong assumptions, naive Bayes is actually much better when you have a small amount of data. But as your dataset grows massively, that exact same naive assumption starts to hold the model back. And that's exactly when you switch to logistic regression, which can use that huge dataset to draw a much more flexible boundary.
Now, it's really important to remember that it is definitely not perfect. You absolutely shouldn't use it if your classes depend on complex feature interactions. Like, if a class relies on feature A and feature B interacting in a specific way, like an XOR pattern, naive Bayes will completely miss it because it literally can't combine them nonlinearly. It also gets super confused if highly correlated features start offering opposing evidence.
So as we wrap up this explainer, I wanted to leave you with a final thought to chew on. Are you throwing massively complex models at simple problems? Understanding why a mathematically wrong model works so beautifully really teaches you that the ultimate goal isn't necessarily finding the perfect equation, but rather finding the best bias-variance trade-off for your specific data. So the next time you're building a classifier, is it time to be just a little naive?